Unified dynamics. Distinction theory.
Traditional physics models depend on dozens of arbitrary parameters, constants we must measure and manually insert to make the math work. These models reach their absolute limit at the shortest distances, where the assumption of continuous spacetime breaks down. Unified dynamics provides an alternative. It models the universe as a background-independent, simplicial pre-geometry, where the sensation of continuous space is an emergent statistical state. Physical reality is treated as an algorithm operating over a discrete network of K4 tetrahedra. This network is defined by a finite combinatorial structure, 4 vertices and 6 edges. If the substrate of reality is inherently discrete, then every physical constant should be a necessary geometric calculation. This implies that the universe possesses 0 free parameters. We will evaluate the predictive validity of this 13-layer theoretical stack by executing 3 rigorous derivations with absolutely no experimental tuning. We will derive the gauge couplings, the early universe's spectral signals, and black hole thermodynamics. These results will then be tested against the F6 computational pipeline, a 9.76 million sample simulation built to identify any structural failures in the theory. Completing these tests would demonstrate that the universe is not a continuous fabric, but a statistical expression of finite geometric capacity. The K4 network is anchored to 2 invariants, a state space dimension of 192 and a primitive topological overlap deficit of 7. The ratio between them, 7/192, is the master scalar that dictates all microscopic scaling. Every physical value scales according to this specific ratio. The matter sector has 5 independent degrees of freedom: burden, phase, closure, framing, and boundary. To maintain topological stability, any interaction distributes its intensity across these 5 channels. Dividing the master scalar by 5 yields 7/960, the bare fine structure coupling. To form a stable, neutral seed, a packet must traverse all 6 edges of the tetrahedron while canceling the 7-unit overlap deficit. 6 times 7 plus a self-consistency unit gives us the neutral seed threshold, 43/7. To lift that seed into higher mass families, the network normalizes 16 binary orientations, adds a burden increment, and rebates a coherence quantum per edge. This generates the universal heavy lift, 101/6. These particle mass ratios and couplings are not arbitrary settings. They are the calculated limits of the tetrahedral skeleton. Scaling up to cosmology, we encounter a phase transition called a closure avalanche. This rapid geometric expansion functions as the framework's version of inflation. This process is regulated by omega convergence. As the network reaches its stable fixed point, it suppresses large-scale fluctuations along the k-axis, breaking the exact scale invariance of the expansion. The effective mass generated during this convergence creates a red tilt in the fluctuations across the cosmic network. The scalar spectral index begins with a bare value of 0.9300, derived from projecting the overlap deficit onto the combined capacity of the vertices and edges. Renormalization group flow then dresses this value to an infrared effective result of 0.9685. This same geometric interplay yields a primordial tensor-to-scalar ratio of approximately 0.01765. These signatures in the cosmic microwave background do not require a separate inflaton field. They are the native residuals of the initial geometric overlap. In extreme gravitational environments, the network reaches its Vertex Information Capacity Limit, a point where no more burden can be localized. The event horizon emerges as an effective surface where the transport speed of the discrete lattice drops to match the local escape velocity. Internal routing is severed at this limit, forcing the system to route and redistribute the 5-component carrier state horizontally across the horizon. Because local transport dynamics strictly conserve information, data is never destroyed during collapse. It is redistributed through entangled states to the exterior. The Bekenstein-Hawking entropy formula arises here. It counts the specific number of independent carrier states mobilized on the horizon to ledger the interior information. Both extreme gravity and black hole radiation are simply the macroscopic results of these strict microscopic data routing constraints. Verifying these derivations requires massive computational testing. The F6 pipeline processes the geometry rules across nearly 10 million independent state update samples. The simulation monitors stability across varying graph granularities to check for any violation of the capacity floor. At iteration n equals 6, the network exhibits a uniform chaotic distribution. This represents the pre-generational vacuum, but at the n equals 7 iteration boundary, the simulation records a sudden transition. Stable topological packets form with a 94.07% closure rate. This n equals 7 boundary identifies a computable topological Big Bang, the exact level where the network achieves the metric convergence required for observable matter. The F6 results validate a scorecard of 28 exact predictions. This includes the standard model constants, the spectral index of the early universe, and a Higgs boson mass of 125.0 GeV. The framework successfully bridges pure discrete combinatorics to observational astrophysics without relying on a single fitted parameter. These results suggest that continuous spacetime is a coarse-grained approximation of a more fundamental, capacity-limited discrete information engine.